Alright, so welcome to another AQA economics video. We've now finished the group 2 topic. Also, I just want to say I'm wearing retainers, so it's a bit hard for me to articulate the T's and I's and all that. So apologies if it's a bit difficult for you to completely understand everything that I'm saying. Hopefully, they can fully understand everything that I'm saying now as I'm speaking. But if you kind of see I'm kind of struggling to separate the D's and the T's, that's the reason why for it. But yeah, as I said before, we're nearly done with inorganic chemistry. There's only 3 topics left, and it'll be in this group 7 topic. I'm pretty sure there's more to do with the period 3, but I think I see more year 2. So yeah, I'm gonna just get straight into this video, right? And yeah, we're nearly done with inorganic chemistry. It's really quick. So halogens are found in group 7 of the periodic table. Halogens are located in group 7 of the periodic table. They're non-metals. They tend to form negative ions called halide ions, and the halogens made up of fluorine, chlorine, bromine, iodine, and acetine. Now, halogen phases, so as you go down the group, the phases change, and there's a reason for that. But generally, it goes from being gases all the way down to solids, and fluorine and chlorine are generally gases, and then bromine is a liquid, but it's kind of like it's a kind of gas. It kind of changes in between gas and liquid phase if you actually look at it, and it's a liquid generally at room temperature. Obviously, these are all accounted for at room temperature. That's the standard that we use, but it very easily evaporates into a gas. But iodine and acetylene are solids. And I actually show you a video by Nal Red, who's kind of shows you a better example of bromine.
Everything around it. This is bromine. This is bromine. It's chemically very similar to chlorine, except chlorine's a gas and bromine's a liquid. It also lets off a lot of nasty orange vapor, and this is why I sealed it in glass. Bromine's really dense, and it's more than 3 times as dense as water, and this makes its vapor really heavy. Bromine's notoriously difficult to store, and if I just put it all back into a bottle or something, it would damage everything around it. So I have to seal it again in a glass ampule that I made from a test tube. This is bromine. It's chemically very simple.
Alright, so that's it. Yeah, check out Nal Red. I think everyone knows who Nal Red is by this point. Very big channel. And that's it. So there's a reason for this. And I think do I go through it? Yeah, I go through it. But you can clearly tell they're all under the same. They're all p block elements. So halogen electron configurations are shown here below. These are 3p to the power of 5. Obviously, I mean I couldn't get the power there, but you guys know what I'm trying to say here. And you can notice if you can clearly notice a trend here, right? All in the p orbital because they're obviously p block and p5 as well. So 2p5, 3p5, 4p5, 5p5, and you can obviously clearly see that trend there. And halogen formula. So halogens all tend to exist as diatomic molecules. So F2. It's not just obviously oxygen. It obviously isn't a halogen, but it's obviously diatomic. But that's just one example. All halogens are described as being diatomic. So fluorine, chlorine, bromine, and iodine, and that's just to do with the bonding. Obviously, they have they have 7 electrons in the outermost shell, so you just need 1 more. And the best way to get that 1 electron is from having another fluorine or another chlorine that's next to it, and then you can form that diatomic covalent bond. Or diatomic, well, a covalent bond to make a diatomic molecule. Had to rephrase that, sorry. And yeah, so properties of group 7 halogens. In this section, we're gonna kind of cover and explore some core trends in the properties of the halogens, and I'm gonna cover electronegativity, boiling point, and solubility of silver halides. That's generally quite a big part of it. I don't know if that's year 2 or year. If I have to go in depth in year 1 or year 2, I think that's more year 2. But I kind of need to. Some of these, I have to understand that some of these things here they really focus on it in year 2, but it's kind of like understanding it in year, just being able to understand it in year one. I realize that some of the videos aren't as in depth as I'd like to be, so that's something that I need to improve on. But generally, all you need to know for AS is electronegativity, boiling point, and then the solubility of silver halides. I don't think you need to know examples like you do in year 2. But in case I'm wrong, I will double check. Halogen electronegativity, right? So electronegativity is how strongly an element is attracted to a bonding pair of electrons. And you should, in a covalent bond. I should have said in a covalent bond, as that is important. And they are in a covalent bond. Remember, they're diatomic, so they have that covalent bond feature. And you should already know this, that you should already know that fluorine is the most electronegative element. I'll leave a link in the description when I talk about electronegativity in the Pauling scale. Fluorine is the most electronegative, and it's generally regarded as a standard. It has an electronegativity of 4.0 on the Pauling scale, but you don't need to know that. All you need to know is that fluorine is the most electronegative element. And electronegativity decreases as you go down group 7 because atomic radius increases, and so electrons experience less attraction to the nucleus. Electrons become further away from the nucleus, and so experience a lower attraction. And also there's also the case of electron shielding as well. That would affect that electrostatic attraction between the nucleus and the valence electrons on the valence shell. So all of these will weaken that, and therefore the electrostatic attraction between the nucleus and, because it wouldn't be the valence section, it would be the bonding pair of on another atom, right? Or forming that bonding pair, right? So all of these, as you go down the group, obviously increasing the number of shells, and so that electrostatic attraction is decreased, and therefore its ability to attract a lone pair of electrons, or whilst being in a covalent bond, would decrease as you go down the group, because our atomic radius has increased. And yeah, this means electronegativity is lower. Halogens boiling point. So boiling points increase as you go down the group. So at room temperature, fluorine and chlorine are gases, as I said before, bromine is a liquid, and iodine is solid. But this is because elements have more electrons as you go down group 7. So the benefit of having more electrons in this case is that, I say benefit, one of the other traits, we said before that they would have low electronegativity, but their overall structural stability would increase because when you have more electrons, you form more van der Waals intermolecular forces, and if this causes an increase in van der Waals intermolecular forces, and it'll be stronger van der Waals intermolecular forces, which means greater. If there's more van der Waals intermolecular forces, more energy is needed to break every single bond between the van der Waals intermolecular forces to break it down, and therefore it's generally regarded as being a more structurally stable crystal, and it will have a higher boiling point. So as you go down if you go down, there'll be more electrons, and therefore they'll have stronger van der Waals intermolecular forces. Fluorine would have the weakest because it has the least amount of electrons, so it would have the weakest van der Waals molecular forces, and iodine and acetate would have the greatest because it would be pretty much solid because they have the greatest number of the two greatest number of electrons in group 7, and would form the strongest van der Waals intermolecular forces. And the last topic is just talking about the silver halide solubility. So I feel like it's more for year 2, or I'll cover it later on. All silver halides precipitate out of aqueous solution. So when ammonia is added, they may dissolve again, but solubility of ammonia decreases as you go down group 7. So an iodide, if you see an ionic compound with iodide, it's least likely to be dissolved with ammonia, and that can be used for testing. I'll probably go in more detail about this in another video. It's used for testing when you have chlorine, bromine, and iodine. You get either a white, a cream, or a yellow precipitate. But anyway, that's another video that I'll go through. But yeah, that's generally what you need to know for halogens, right? And trends of halogens, as I said, we're just going against reviewing everything that we went through in this video. So the trends of halogens down the group is that electronegativity decreases as you go down the group. Solubility of silver halide decreases as you go down the group, but the boiling point increases as you go down the group. And obviously we have the phases here. Gases, fluorine and chlorine are gases, bromine is a liquid, and iodine is a solid. Thank you for listening.